the Chem 1 class on absorbance and concentration, a short introduction to our lab that's coming up on Wednesday. And the law that describes absorbance and concentration is known as the Beer-Lambert Law, and sometimes it's just called Beer's Law. I think I've joked about this before. If you make a scientific discovery, make sure you're the first name. Otherwise, your name might get dropped from the popular way of describing that law. This law is relatively simple. It's going to play a bit of a role in the lab, and that is that the light that's absorbed by a solution. Oh, sorry about that. If it went black, I hit something that wasn't supposed to be hit. So the light absorbed by a solution, we're going to call that capital A, is directly proportional. Now, remember, that means they both move in the same direction to its concentration. And the concentration we're going to call C in terms of moles per liter, or molarity. So basically, this is saying that as the concentration goes up, the absorbance goes up, and vice versa. If one goes down, the other goes down as well. Now, absorbance is usually going to be measured in something called the spectrophotometer. We actually saw these way back in chapter 5 during our color lab when we looked at absorbance and transmission spectra, and we saw that solutions that were red absorbed blue light, solutions that were blue absorbed red light, and so forth. We'll talk about that again in a moment. So the spectrophotometer measures absorbance, and fortunately for many of you, the absorbance is a unitless number, so you don't have to put any units in it. That's one of the few unitless numbers we're going to get this year. Now, A and B are two things that aren't going to change. I'll describe what they are, but they're not going to change during our experiment. A is the amount of light absorbed per molar per centimeter, and that's going to be something that depends on both the substance, and the substance in this lab is going to be copper 2 sulfate, and we're going to get that pretty blue color of the copper 2 plus. And wavelength is something that's important as well. And so for our lab, we're going to choose 635 nanometers as the wavelength at which we make our absorbance measurements. That's going to be red light, and obviously red light will not transmit. Won't be transmitted for a blue solution, and instead of being transmitted, it will be absorbed. And it's important that when you do write the data tables and write your graph for this, that 635 nanometers, that you specify what wavelength. Otherwise, it doesn't give a complete picture of what the reaction is. So this A factor just depends on the substance and the wavelength. B is a simple thing called the path length. And the path length is, if you look in this diagram down below, the path length is essentially the thickness or the width of the cuvette. And the cuvette was that little device that we used to put into the spectrophotometer. It was square for one of them, and it was round for another one. And we've always standardized on a 1 centimeter path length. And so B down here is equal to 1 centimeter. So what we do, because the A and the B are not changing for us, we're going to combine them both into the slope of the best fit line. This is going to be a linear relationship, as all direct relationships should be. The slope of the best fit line, where M is equal to A times B, and that B has nothing to do with the MX plus B. This is just our way of talking about this particular experiment. And so what we're going to do is make a best fit line out of the data that we're going to get. And we'll talk about that when we talk about the lab itself. So what you're going to do is plot as a function of the concentration, you're going to plot the absorbance. And you should get a line or something that very closely resembles a straight line. And you do want to have 0, 0 as a point too, because after all, zero absorbance, you don't expect any light to be absorbed when you have zero concentration, which means pure water. So you do expect zero absorbance. And you can see that the data that we have here fairly well represent a straight line, and your data should too, since I'm going to be giving you relatively good data with only a little noise built into, random noise built into it. All right, so what happens is we have this incident light. This incident light, that's the 635 nanometer light. And this is a red solution. It should be blue, but go with it. So pretend this is a blue solution. And what's going to happen is the transmitted light is less. And because the transmitted light, the amount of light that's transmitted is less, that means we have a high absorbance. We're measuring a relatively high absorbance. And that absorbance should be proportional to the concentration. And that's what the straight line is saying. So the straight line is A times B. The slope, as I said above, slope is A times B is equal to the slope of the line. The y-intercept down here should be 0. And it's going to be close to 0. And if we were to do any math with it, which we're not, we would probably set it equal to 0. We're going to be interested in what that slope is, but we're also going to be interested in being able to read the graph. And one of the reasons for that, and this is how we're going to apply it, one of the ways we're going to apply this in the lab, is I'm going to give you a sample absorbance. Now, this is important because you've got to get this the right way. If you do it the wrong way, you're going to get this question wrong. Suppose I were to tell you that you have a solution of unknown concentration with an absorbance of 0.4. Here's where Beer's law comes in. Now, you can use the slope of the line and the equation for the line, and if you really want to try that, I'll let you go ahead and do that. But what I want you to do is read this off the graph. And so what you're going to do is take a straight line from your 0.4 absorbance all the way over to the line itself. Don't look at the points that are off the line. Look at that line itself, because this line, as we talked about in the past, is like an average and getting rid of that random error. And then you take from that line, you drop the vertical down to the x-axis. And at the x-axis, we're going to read off what the concentration is, or would be according to this line. And this looks like it's a little bit to the right. I would say like 0.205 molar would be the concentration that I might read off of this. Hopefully your graph will be a little bit more precise. I think I've made it that way. So this is what Beer's law is all about. Absorbance of light is directly proportional to the concentration. And there will be a couple of questions about that in the lab. So for the lab, make sure you watch the video that I've provided you for the lab itself. Make sure you read through the lab and make sure that you answer the pre-lab questions. They're all calculations 1A, 2A, and 3A. And we will see you in class next time.